Good day, everyone. Thank you for joining us for the second installment of our 2025 webinar series. My name is Lori McLeod, President of NOVONIX Battery Technology Solutions, and I'll be your monitor for our webinar today. For those of you wondering, the session will be recorded and posted on our website. In just a few moments, we'll be hearing from two of our NOVONIX team members, Dr. Stephen Glazier, Director of Technology, and Ken Broom, Senior Director of Business Operations. Since 2018, Stephen has been working to scale the R&D services team and cell prototyping and test capabilities. He oversees R&D programs which span the entire lithium-ion cell development space, including NOVONIX's own materials and high-precision coulometry equipment development, scaling and validating technologies for our customer programs, and industry collaborations. Beginning in 2017, Ken led the development of the cell prototyping facility at NOVONIX. He has worked in the lithium-ion battery industry for 35 years, operating as COO at BAK Battery in China and General Manager at E1 Mali Energy, directing manufacturing, engineering, and plant scale-up, product development, and R&D functions. Today, Stephen and Ken will be discussing NOVONIX Battery Technology Solutions R&D services offerings, including end-to-end cell prototyping, testing, and evaluation to help our customers bring their concept to market. Following the presentation, we will leave some time for questions. You can leave them directly in the Q&A feature at the bottom of your screen, and we will respond to as many as we can. Now I'm going to turn it over to Stephen.
All right, thank you, Lori. All right, so I'm just going to start out this webinar with a brief introduction to the NOVONIX Group. So the NOVONIX Group has a few different main focuses. Some of you are familiar with some more than the others, so I'll go over all of them. So starting out on the left side here with our anode materials division, where we are scaling and mass manufacturing our synthetic graphite for the North American lithium-ion industry. This division has offtake agreements with Tier 1 manufacturers, such as Panasonic, PowerCo, and Stellantis. Our NOVONIX Cathode Materials Group up here in Halifax, Nova Scotia, is commercializing a patented all-dry, zero-waste cathode synthesis technology. And then the rest of our Battery Technology Solutions Group in the Nova Scotia, Halifax, Nova Scotia area is focused on our ultra-high precision coulometry cell testing equipment that we design, make, and sell across the battery industry worldwide, as well as our R&D services solutions with our pilot prototyping line, cell testing, and collaborative projects that we help the entire battery industry with. And that's what we're going to be diving into more today. So I'm going to start by talking about the gaps that exist in the industry right now and why we have this part of our business. And we've identified that there are some big gaps, especially right now in the battery industry, where especially in North America, everyone's really having to focus on their core competencies, their core technologies, and there's other aspects of proving these things out that are quite distracting or cost intensive internally. So having that knowledge, the dedicated staff for every process internally is a really big hurdle and a big gap in the industry. Access to talent, recruiting certain talent and expertise, and the diversity of experience, being able to tackle different problems and having exposure to all these different types of materials and problems in the past is something that's very difficult to find people with that knowledge. And then some of the big ones right now, CapEx and OpEx, to build up a quality, very small scale prototyping line to make really repeatable, confident cells, get good results quickly, is at least $3 million, needing dry rooms, slot die coating equipment, testing equipment, assembly equipment, and then of course installation and lead time at this point can be upwards of a year for certain pieces of equipment. And then just to house all of that, have utilities and maintenance, dedicated technical staff, the overhead there. And then a really big aspect is time to commission and validate the processes and really trust the results coming out of your line. So our biggest goal with our R&D solutions or R&D services division is to make your investment go further faster, rather than having to do all of this in-house and have all of this kind of all these redundant facilities all over the country of everyone trying to do the same thing to really help people achieve those goals quicker. So we really try to address all of those gaps. We have a team of experienced battery scientists. We have 15 master's and PhD battery scientists with experience from all over the industry, from R&D to mass production, from EV companies to cell companies. Our fully equipped prototyping facility, over 3,000 cell cycling channels, and a large variety of different projects that we've completed with customers. And this helps address all of those gaps. It saves these large expenditures. We have a dedicated production staff. We have people that really know each step of the process and understand how to really fine tune and overcome barriers in mixing and coding versus other dedicated staff that are really interpreting the cell testing results and understanding the electrochemistry. Working with us, you get to leverage knowledge from across the industry. Lessons learned are a huge part of doing R&D, and we have a lot of those behind us. Really highly interactive project management function. So every customer of ours has a dedicated project manager that has a really highly interactive engagement with them, a direct point of contact, and really make sure that the projects and programs are running seamlessly. And we're really flexible in that we can start and end any step of the process, make you cells and test them in-house. You can send us cells. We can send you dry cells. There's a really good advantage to complement anything that you have built up already or stood up in your labs. A typical process with us looks like a discovery call. We establish an NDA and really start to understand your objectives, assign a technical team to the project, including a project manager, a technical lead, which is typically a PhD scientist. We work on your statement of work and quotation, and then we can kick projects off. We welcome customers on site, and a bit of a difference between us and some other prototyping houses is we welcome customers, but you don't have to know how to operate the equipment. All of our staff will operate it. You can be there along for the ride. You can see every step of the way and understand it, consult, and help troubleshoot certain aspects of, say, your technology or material. And we have very frequent communications and touch points through each project. We have informal progress reports, and even I'll talk a little bit later about almost near-time access to your cell testing data. So you can go in, there's almost 100% transparency with access to your data. You can go in and access at any time, make your own plots and reports in the battery data software by Voltaiq. And then, of course, there's the formal final project reports in each milestone. And just again, I'm going to touch on this real advantage of project management where you're not having to chase down certain parts of a technical team or the person that did any one part of the project. You have a dedicated project manager that is your point of contact that understands where everything is in the project and can get all of the answers for you and kind of consolidate that communication. So that's what our process looks like, a very high-level overview of things. I'm going to pass it off to Ken Broom now to take away and talk about the specifics of our pilot line and capabilities and really dive into those more fine details. So take it away.
Thank you, Stephen. So thank you. Thanks. So different project types. We've worked on a wide variety of customer projects with lithium ion, different chemistries, different cathode materials, variety of NMCs, LMFP, LFP, other cathode actives, artificial and natural graphite. With silicon-based anodes, we've done as low as 5% silicon content up to pure silicon anodes. With lithium metal and anode-free, worked on those chemistries. And for those that aren't familiar with anode-free, it means that you put copper foil in place of the anode when you're making the cell, and when you go through formation, lithium metal plates out on the surface of the anode. Done a lot of work with electrolyte solvent mixtures, different electrolyte salts, depending on what type of performance is being looked for, and a variety of electrolyte additives. In the last year and a half or so, we've been doing quite a few projects in the sodium ion space. We've had customers come to us with novel inactive components like separators, current collectors, different binders, and conductive enhancers like graphene or carbon nanotubes. And when we look at how we work with the customers on the projects, there may be, depending what materials they're coming to us with, have to do work on the optimization of the slurry mixing process in order to get high quality coatings. We do a lot of projects. We're doing comparison of customer materials to high quality industry standard materials that we have access to. We've worked with vendor selection for materials or with pack makers working on cell selection. We've done a lot of work on electrolyte formulation to optimize cell performance, done different cell designs for different situations, and we tailor our formation and test protocols to gather the data that's most relevant for the customer, the end result of the project. So as far as the separate cell types that we make, we have 2320 format full and half coin cells. For stacked pouch, we do single and multi-layer stacked pouch cells, and in two different formats. In the smaller format, we end up with a 1 to 3 or 1 to 5 amp hour capacity cell, and the larger format we can get up as high as 20. For wound pouch cells, we have again two formats. The smaller ones are in the milliamp hour range. The larger ones get up to about 3 amp hours. And for cylindricals, we do 18650s and 21700s. And looking at typical projects for us, so we have 2 slot die coaters, and the slot die coating runs can go anywhere from 30 to about 150 meters, depending on what the customer needs, how many cells they want made, or whether they just want coatings done. And for stacked and wound pouch cells, typical quantities 20 to 50, especially if we're doing material evaluations, that's a typical quantity, but sometimes customers want a lot of finished cells or dry cells from us, and we do quantities up to 500. Similarly, for cylindrical cells, typical 20 to 50, and large quantities are around 200. A couple of project examples. We had Mallard Creek Polymers come to us, and they wanted to commercialize an SBR-based binder. And so they wanted a third-party validation of their materials. So they sent us some samples, and we used high-quality industry standard material for a comparator and ran a series of tests, and were able to produce a comprehensive report at the end that they've been able to use to promote their product to potential customers for them. And another project is for anode-free electrolyte optimization, where we're creating a non-gassing, non-flammable electrolyte. And we made a lot of cells to show that we could maintain the performance compared to what baseline is for that chemistry. And both of these can be downloaded, the Mallard Creek polymer one from our website, and the anode-free electrolyte optimization is an open access article. So I was going to go into some detail on our prototyping line next. So for slurry mixing and coating, we use dual planetary mixers for slurry mixing. We have two 2-liter mixers, 2 5-liter mixers, and a 15-liter mixer. The atmosphere in our mixing room, the dew point is lower than -20, typically lower than -25. And we do the usual type of QC checks that you would expect in this type of process. So viscosity checking, solids content, rheology, and grind gauge to make sure that the slurry quality is good. And sometimes at earlier stages, depending on the materials that we're working with the customer, we may even do smaller slurry mixes than this and just do hand coatings, grind gauge, and rheology measurements just to confirm that the material coats nicely before we go to full-scale coating. We have a couple of slot die coaters that can coat up to 300 millimeters wide on 330 millimeter wide foil. One of the coaters has a 2-meter long drying section, the other one has a 4-meter. Each of those drying sections made up of 1-meter individual sections, which have independent temperature control in those sections. The ambient dew point in the coating head area is less than -20 degrees C. And we do the QC checking just to make sure we've got good stability, because we're working with novel materials and you're not sure how the slurry is going to change over time. We're checking the loadings every 10 meters or as per customer request, and we'll also do adhesion testing. So we have 2 ambient temperature roll-to-roll compression machines, and we can, besides checking density as we go along. We can also do measurements like spring back measurement. And this was important in the Mallard Creek polymer situation that I described earlier, because they wanted to make sure that their materials didn't have worse spring back than anything that's already available in the market. We have 2 roll-to-roll slitting machines. Besides our standard widths that we have set up for making our wound products, we can also customize slitting widths if that's something that a customer is interested in. And we're able to slit separators. Sometimes we've had customers come to us with their own separators that they don't have the ability to slit to the width that we need to make our standard products. So we are able to do it in-house here. And for electrode punching, for making stacked cells, we have a semi-automated punching machine. We have a 1,000-square-foot dry room, and all the cell assembly processes in that dry room are analogous to mass production. So it's following the same types of processes, just at R&D scale. The ambient dew point in that room is typically less than -50 degrees C. We have vacuum ovens in there that we use for electrode and cell drying. And we store our electrodes in there when they're in process between coating and compression, and between compression and slitting, and also prior to being used in making cells in the dry room. So as far as the stacking and winding equipment we've got for stackers, we have 2 to make the smaller format cells, and they're this industry standard Z-fold type stacking machines, and 1 for the larger format that I described earlier. And we have 1 semi-automated cylindrical winder and 1 semi-automated pouch winder. For pouch cell assembly, it's the same process steps as you would see in industries of pouch forming. Electrode vacuum drying can be done at this stage or just in the full cell. The semi-auto stacking or semi-auto cell winding, the pouch sealing and trimming, cell vacuum drying, electrolyte fillings done with a calibrated pipette manually in a fume hood in the dry room. And we have the cell vacuum sealing, and then after formation, we degas the cells. And for cylindrical cell assembly, it's similar, but in this case, because we're winding 1 electrode at a time, we cut them to length in the dry room first, and then we do ultrasonic tab welding, do the electrode taping. Again, drying the electrodes is optional at this stage, or it can be done just in the wound cells. We've got the winding like the machines I showed earlier, put the jelly rolling insulators into the can, standard grooving equipment, resistance welding of the anode tab to the can. We have a laser welder for welding the header to the cathode tab, and the vacuum drying at this stage. And again, similar electrolyte filling like you can see in the picture on the right here, and then crimp sealing the cells closed. And I'll turn it back over to Stephen so he can talk about the cell testing that we do.
Perfect. Thank you, Ken. All right. So once all of our cells are made from our pilot line, they can then go on to either into formation after they're filled, or of course, we can also ship out dry cells to our customers. So like I've said before, we have over 3,000 channels of temperature controlled cell testing equipment. So we can do all types of customized formation or cycle aging protocols for our customers. It's really tailored to whatever the customer need is. So we do a lot of cycle and calendar aging, a lot of performance testing, or testing for parameterization of cell models, for example, doing things like GITT and rate mapping, DCIR, HPPC, EAS capabilities, as well as about 400 channels of our own ultra-high precision coulometry equipment. And I'll talk a little bit about that in a few slides. So most of our 3,000 channels are sub 20 amps, but we do have some equipment that can go up to 400 amp 5-volt cell testing. So we do really focus on cell testing rather than pack or module testing in our facility, but we can handle some pretty big cells with safety equipment, explosion-proof chambers, etc. Some other types of testing that we can handle for cells are cell teardown and post-mortem analysis, including some analytical testing on, say, the electrolyte or gas produced or the electrode surfaces. In situ thickness measurements on pouch cells, ex situ gas volume and thickness measurements on pouch cells. and some of the analytical testing I was mentioning here, which are everyone's favorite 3 to 5 letter or 6 letter acronyms, as well as some others that we can work with, both our internal analytical labs, as well as some partners. We also have some external partners that we use for safety testing and CT scanning. One really big advantage that is something that I really appreciate as a battery scientist is being able to get cell testing data at your fingertips. It feels a lot more like running your own R&D program if you can access your data in real time and you're not waiting for it from a third party. So we've partnered with Voltaiq to really bring this to our customers, where you can log in and access your cell data through Voltaiq in almost real time, only a couple hours of delay from when your cell gets put on test till you can see those first data points coming through, processed, build up your own reports, explore your data. There's full transparency into what's going on with your cells and data. So I'm going to take a few minutes to talk about NOVONIX ultra-high precision coulometry, because this is something that we put into almost every single one of our services projects, and this really helps customers get really early results and insights, and sometimes very deep results and insights into some of the degradation mechanisms or performance in their cells quickly. So ultra-high precision coulometry is the highest current and voltage accuracy and precision equipment available for cell testing. We've been making and selling this equipment to the battery industry since 2013 or so. And I'm not going to go into a big deep dive here, but you can learn more looking at some of our past webinars with the Volta Foundation on YouTube, and also some webinars that we've done with Voltaiq on their YouTube channel. In a nutshell, this precision and accuracy allows you to get a lot more information, or a lot more fine-grained information, in a very short amount of time. So this precision and accuracy allows you to take metrics like coulombic efficiency and see differences very, very quickly with high degree of confidence, not relying on long-term trends over months of cycling or large amounts of cells to get enough statistics to make decisions. So here's a plot showing a few different cell cyclers. 1, 2, and 3 here are cyclers that are very common in R&D labs. We have them all in our facility that we actually use for our research programs, including over 1,500 channels of cycler 3 here just in our building. So there is definitely a place for every single type of cycler, but we really use the NOVONIX UHPC to get those really fine insights quickly. So you can see here, this is 8 identical cells tested on each of these units, and these envelopes here are showing twice the standard deviation, just showing the kind of that spread of data in these cells that are tier 1 18650 cells that should be identical in performance, but the inability of these other types of equipment to really identify that these cells are exactly the same. So if you're doing quick iterative work and trying to, to look at new formulations of electrolyte, or do vendor selection on cathode materials and understand which material is more electrochemically stable, or how do these perform at these different operating conditions, the UHPC is going to be able to tell you that in just a few cycles rather than waiting months for these trends to appear. So this can be done by cycling cells and using really accurate cycle metrics to look at trends very quickly. We've seen a lot of customers start to use UHPC for quality control in their labs and mass manufacturing to do statistics for inter and intra-batch variances and thresholds. And with all of that accuracy and precision comes really nice raw data. So unparalleled DQDV resolution, no need for smoothing, very easy to see small differences or degradation mechanisms. And then, of course, lots of other things. Impedance and diffusion measurements become a lot easier with very clean data, advanced modeling and lifetime prediction, which you can learn more in some of our other webinars that I've discussed in the previous slides. So to bring everything kind of together, I'm going to show an example of a short project in evaluating different cathode materials that we did from coin cell to full cell using our UHPC, as well as some of our long-term cycle aging type experiments on full pouch cells. just to bring everything together. So the goal of this project was to identify as quickly as possible and then prove out the which of these three cathode materials was going to be best for an application purely based on electrochemical reactivity. So we have cathode A, B, and C, and right away upon receiving these materials, very quickly we can turn around some coin cells, and instead of cycling these and trying to tease out some cycle data, we put them through this kind of stress test on UHPC where we did a constant voltage hold and teased out parasitic current, the current needed to, once all of the kinetics have equilibrated within the cell, to maintain that voltage for these materials. And this rate of this current that we collect is essentially analogous to the rate of electrons we're stripping out of some things like the electrolyte or related to transition metal dissolution in the cell, electron donating reactions that are showing higher reactivity from these cathode materials, and basically measuring those directly. So we can see in these early results, just within days of receiving material at our site, that cathode B here has a much higher parasitic current, followed by cathode A and cathode C. And so this is measuring microamps. If you see the scale over here in these cells, these are very small current values. And even though the data look a little noisy here, all of these data are very real. So the UHPC accuracy and precision at this level is less than 10 nanoamps. So all of this noise is little fluctuations due to small oscillations in voltage, say, in response to that, or temperature. But we can rely on these values to make these decisions. So the hypothesis here would be, once we make these materials into cells and start testing those, that we'll see a failure in cathode B due to these types of reactions first. So then after about a week of coding and building cells, getting cells onto formation, and then into UHPC testing and sticking cells on for long-term cycle aging. In our UHPC testing up here, we can see just in 10 or 15 cycles that our coulombic efficiency is much lower for cathode B, which had that higher parasitic current. And something that I cover a lot in the webinars that I've mentioned are that you can take coulombic efficiency and split these into some more useful metrics with this high precision data, such as this one called charge endpoint capacity slippage. Not all coulombic efficiency is due to capacity fade. There are other contributions that aren't really possible to split out on other types of cycling equipment. So when we split this out into the components of coulombic efficiency, we see that the capacity fade of these cells that we've made, these are 1 amp hour pouch cells off our pilot line, is more or less identical after 20-25 cycles. But we have this big contribution to this lower coulombic efficiency coming from this term that's associated with these electron donating reactions, electrolyte oxidation at the cathode, transition metal dissolution, things that the cathode is contributing to the system. And we notice that this is much higher, these rates of reactions from cathode B, agreeing with our coin cell data that we collected just within a few days of receiving material. So now we're getting more and more confidence that we've been able to rank these materials just within a couple weeks. And then after months of long-term cycle aging on multi-amp hour cells off our pilot line, we start to see these trends appear. Cathode B fails first within a couple months of cycling, and then 6 to 8 months later, we see cathode A and B start to split up. And this is type of work that we were able to, with the synergistic effects of the pilot line and the high precision coulometry equipment, that we were able to see just within days, but then validate for our customer within months of actual cell testing. So hopefully that gives a good idea of the timelines of getting some information and kind of the full scope of a simple project that we can do here. So just to kind of summarize and reiterate, we can do projects that are simple statements of work or very progressive statements of work over multiple years, sometimes with some customers, as well as some highly collaborative special projects where we really get involved with your teams. We contribute to the same intellectual property, very, very collaborative types of and flexible types of projects we can do. And again, we can do any subset of our offerings. So receiving electrodes and we make the cells, receiving powders all the way through to sending you dry cells. We can really enter and exit the process wherever it makes sense for your needs. So let's collaborate. If you have any of these gaps that you're trying to address in any of your programs, whether that's knowledge or CapEx, access to equipment or personnel, reach out. We'll find out how to collaborate together and help you scope your project and get the results you need.
Thank you, Stephen and Ken. Before we launch into the Q&A, just a reminder that if you do have questions, to submit them using the Q&A button at the bottom of your screen. We've received some interesting questions thus far, so let's start with what materials do you use, and do you offer NOVONIX materials in your projects? Stephen, I'll throw that one at you.
Sure. Yeah, so in terms of the materials that we use, if a customer, let's say we have a cathode active material customer, somebody that's developing active materials in the cathode space, and they need to compare to some anode material and they don't have access to that, then we do have many different types and specs of active materials that are industry standards. So these are recognized brands and manufacturers and models of materials. We typically don't offer the NOVONIX cathode or anode materials in our projects, as these are highly tuned and being developed for specific customers for these offtake agreements that I discussed earlier. So we don't necessarily have a fixed menu of materials to pick from like some of the established recognized materials in the industry. It also allows your customers and your partners to recognize the materials that we're using if we use something that is already standard and known in the industry.
Okay, thank you. Another one for you, Stephen. Do you offer large format cell testing?
Yeah, that's a good question. So we do. I mentioned briefly that we have a number of channels that can go up to 400 amps of 5-volt cell testing. And those are available to be tested in explosion-proof safety chambers. And so we have some capability to do that. And of course, there's a lot more nuances that go into testing large cells. So we scope that out with our customers to understand the exact needs and fixturing, how many cells may be able to be tested per chamber, et cetera. So yes, we can do that.
Okay, thank you. Ken, do you offer dry solvent-free electrode fabrication?
Not at this time. No, we don't. We're working with a couple of customers on that type of process, but we don't have the capabilities in-house at the moment.
Okay. What information do you use from EIS and GCMS, Stephen?
Sure. Yeah, for GCMS, we've done a number of projects where we're looking for certain types of gases, either through formation or long-term cycle aging, to determine really what types of components are breaking down within the electrolyte of the cell. So that would be for both gas and liquid GC. So looking for what is being consumed from the electrolyte in something like liquid GC, is the composition changing over time? For EIS, typically looking for doing some basic fitting and understanding where changes in impedance are coming from. If this is more contact or SEI based or diffusion based. So again, really tailored to our customers' needs, and we'll scope things out directly to a customer's asks or wants, or we will consult on what might be the best testing if a customer is unsure.
Okay. Next question. If I provide a lithium-based cathode formula, would you be able to synthesize and characterize it and analyze its potential?
So this is direct specifically for cathode, like synthesizing a cathode material, I would assume, or that's how I'll answer the question. I would say for that, it would be best to reach out to our cathode materials team and look at ways of potentially collaborating there. And then we would have the opportunity to move that into the services division. Currently, we operate separately from our cathode materials synthesis team that is really commercializing a cathode process. But yeah, we can be involved in other types of collaborations, or once something moves from when you get it synthesized, it can be brought to us. We're mostly on the receiving side of in a powder format, moving into synthesizing cells and doing the testing and interpreting the data.
Okay. Another EIS question is, what software do you use to analyze the EIS data?
Yeah, so in-house, we have both biologic and Gamry systems. So it's a combination of internal analysis tools and scripts that we've written to do some basic things, as well as some of the manufacturer provided software to do equivalent circuit modeling that we'll use. We've also incorporated the Gamry EIS products into our NOVONIX UHPC systems. So that gives us the opportunity to do some interesting types of automated testing, and insert EIS into our UHPC testing as well. So I just wanted to throw that in there as a quick pitch.
Do you perform thermal runaway tests?
We do not, but we do have a partner that does these tests. The partner is in the US. So we can do both accelerating rate calorimetry with that partner, as well as things like nail penetration and crush testing.
Okay. Do you offer any simulation types of solutions like electrode, electrolyte modeling at the molecular level understanding?
Yeah. Currently, we don't do any like quantum chemistry based work. So we do have contacts through the industry that we can talk to, and we do offer a pretty like highly collaborative opportunity with some of our partners. So getting others involved to really leverage their expertise in a certain space, while then we leverage our expertise in, say, doing the actual experiment. Because as I alluded to in some of the opening slides, it's really key to work with partners that have really key expertise in one area and leverage those to give really complementary path to success. So yeah, there are opportunities to work with certain partners, and we can all kind of work together in a whatever method works best to achieve your goals.
Okay. What's the minimum quantity of active powder typically needed to make a few prototype cells using your slot die machine? Ken?
So for cathode materials, it's about 2 kilos, and for anode materials, it's around 1. And that'll get us probably about 10 meters of whichever we're making, anode or cathode.
Okay. Thank you. Will you be able to do performance testing up to 100 amps for large format cells at different temperatures and for long durations, so 6 to 18 months?
Yep. Yeah, we'd be able to do that. So yeah, shoot us a message and we can talk about that scope of work. Again, there's some nuances in terms of sizes and dimensions, how we're going to fixture them, but those are all easy to overcome.
Okay. What is the max web width you're capable of coating? Ken?
The maximum width of foil we can run in our coater is 330 millimeters wide. And coating widths, we've coated up to 300 millimeters wide on the 330 millimeter wide foil.
Okay. How much cycle can be tested for EV applications in NMC chemistry and LFP chemistry?
How many cycles? I mean, we can
Yeah.
test cells as long as a customer needs. So we'll set up those expectations at the beginning of projects. We can be very flexible in how we scope those out, whether we say we're going to cycle these until they reach 80%, or we're going to go a certain number of cycles or a certain length of time, or overshoot and then only invoice, let's say, for the number of the amount of time that the cells actually last for. So we can be very flexible with that. We always aim to have more channels than we need so that we can be that flexible for our customers. So yeah, we don't have any issue being really nimble like that and doing, even committing to very long-term projects.
Hey, Ken, this one's for you. How do you assure the quality of the produced electrode rolls? Do you have inline characterization tools?
We don't have inline characterization tools, but what we do is based on starting at the slurry stage, we have very specific QC checks that we do through there to make sure that the slurry is mixed well, and evenly throughout the slurry, and that the slurry rheology indicates that the slurry is going to be stable throughout the coating process. And then when we're coating, we're manually checking the loadings every 10 meters to make sure that nothing is changing. So we've dialed in the coating speed with the die gap and everything for setting up the coating initially, to make sure that things are stable throughout. And then we also do the adhesion testing to make sure that there's no issues there as well. So, but nothing in line. It's all done either during or after, but external as opposed to inline.
Thank you. How quickly can you go from receipt of material to receiving data analysis, Ken?
So from receiving material through to getting the coatings done and cells made, and then through formation to get the first data is it depends on our coating queue, but it can be in the range of 3 to 5 weeks.
Can you, when you're running a project with the customer, who owns the IP that is generated from the work product, Stephen?
Yeah, so all of the IP is owned by the customer. We have very favorable terms and conditions that we've set up for the customers, where everything that comes into our building, all of your knowledge and know-how is protected, and that you own that IP, so that there are no issues there. In some special cases, like I alluded to, we've set up some in the past special collaborative projects where we're actually kind of building things together, in which case we'd look at kind of a custom set of terms and conditions and agreements on more of a collaboration or partnership. But for almost, I'd say 95% of our projects go through our standard terms and conditions, which is you own all of your IP and the outcomes of the work.
Okay. Do you use SBR binder and why? And secondary, what is the comparison with PVDF and PTFE?
So for anodes, we use SBR binder because that's basically the industry standard now. For cathodes, we continue to use PVDF. So and so those are the two binders we're using primarily. So just because those are industry standard.
Yeah, we have run other projects with companies looking at novel binder systems, but in terms of materials that we would provide for a standard project, then yeah, we would be looking at CMC SBR, like I said, for anodes, and PVDF for cathode.
And what is the typical and maximum mass loading you can achieve for the electrodes?
So our typical in terms of milliamp hours per square centimeter is around 4. But we've got up as high as close to 5. But then you start to run, when you get much higher than that, you start to run into problems with the electrodes cracking during drying, and really slow coating speeds as well. So it's a typical around 4 is but up as high as close to 5.
Just a follow-up question on the one previous. What makes SBR standard for anode and PVDF for cathode?
SBR because it's water-based, and the industry switched to SBRs probably about 20 years ago because they wanted to reduce the use of NMP primarily, and not having to deal with collecting that and reusing it in mass production. And they haven't, because of the reactivity of the cathode materials with water, there's no water-based replacement. So we're still using NMP and PVDF with the solvent recovery systems associated with that in mass production.
And issues with electrochemical stability of using like CMC SBR at the high voltages of the cathode.
Are you limited to using commercial electrolyte formulations, or can you provide unique electrolyte blends?
Yeah, we make all of our electrolytes, or most of our electrolytes, in-house if a customer is not providing the specific materials or pre-mixed blends. So we have a couple different electrolyte partners that we can order a bespoke custom electrolyte. We can blend them in-house. We have dozens of different solvents, additives, salts in-house, from really standard things to kind of wacky stuff that we've ordered in for specific projects, or even just to make sure that we have because we read it in a cool paper somewhere.
What types of conductive additives are being used in cathode and anode electrodes?
Depends on the materials, like the active materials themselves, but with NCMs mainly, we're seeing things like Super P being used, and for the anodes it's mainly Super P. With electrodes like LFPs, we'll see CNTs put in them. We'll also see CNTs put in silicon anode graphites to improve conductivity as well, but generally Super P is used in everything in different quantities.
Okay. Do you provide failure analysis or consulting services to support in-house cell manufacturing troubleshooting?
We've done that in the past, not so much in helping with plant troubleshooting, but we certainly can do that. We've done it more in context of customers coming to us, often battery pack companies who want to understand failure analysis of the cells they're seeing in the field. And so we do the disassembly analysis and provide reports on what we find.
How do you define full and half cell?
Yeah, for full cell and half cell, when we're defining half cells in these presentations, we're talking about cells with lithium metal as the one of the reference electrode, and then say our active materials such as graphite or NMC or whatever cathode material we're using as the active electrode. Whereas when we say a full cell, we're not using any lithium metal, and we're using an actual active cathode and anode material, like doing a graphite MC cell. So we do most of our engagements start off with half cells, lithium half cells, so that we can measure the specific capacities, irreversible capacities of the customer materials and design the cells properly with proper N to P balances, and just really to understand the expected performance. We can also do full cell coin cells, especially if there's not enough material to make amp hour level cells. So we have had projects where we can only receive grams of material from a customer and can make full coin cells and cycle those with a reference cathode and a customer's anode, or vice versa. Yeah, so we really have kind of flexibility around all of those options.
I just want to back up to the previous question a little bit about the cell disassembly analysis and troubleshooting. So depending on the state of the cells we receive, meaning, are they still working cells, or are they not working cells, and so on, we would also consider making use of our partner for doing CT scanning to help with the diagnosis of the internal problems with the cells.
in those cases, we have employed UHPC as well to look for any differences or variability between cells and degradation or active materials, small differences in capacities or self-discharge levels, just to see if there are things we can identify with the really precise electrochemical data in the short term.
Can you speak to the standard electrolyte composition that you're using?
Yeah, the standard electrolyte composition may vary depending on the customer. Let's say it's a silicon anode customer. We'd obviously have an electrolyte with a certain amount of FEC in it, whereas if we had a customer looking at only a graphite anode, maybe there's only a small amount of FEC or just VC. Typically, though, if we're looking at, say, just a graphite NMC project, our standard electrolyte would be something like 1.2 molar LiPF6 in EC, EMC, DMC, 25 to 5 to 70 by weight, and with a certain amount of vinylene carbonate as the baseline additive. But again, we tailor this to every project depending on what the outcomes are. If we want to really quickly see the effects of electrochemical degradation, we may stick to a simple electrolyte like VC only. If we want to really make and optimize a system for a customer, then we'd look at making more advanced, high-performing electrolytes, add in more electrolyte additives, some salt additives or sulfur-containing additives, change around the solvents, especially if we're looking for lower temperature or higher temperature applications.
For half cell materials testing, what type of separator is needed to be used? And what is the best separator for high rate testing?
Yeah, we use a variety of separators in our half cell, typically using like a CellGuard or BMF, blown microfiber separator, sometimes combining different types of separators together. So it really depends on the materials that we're using and the application. Yeah, so that's
okay.
Yeah, it varies.
Yeah. All right. Thank you. And we'll close the Q&A session with this. I think this is a good fitting question for the last one. What is the most interesting trend you are seeing in cell materials, cell manufacturing, or cell technology?
Ken, do you want to go first, and then I'll think of mine?
Sure. Thanks, Stephen. Yeah, so I think from a cell manufacturing perspective, I think dry coating is really one of the most intriguing. We hear lots about it, but it's being held very close to a particular company's chest that tends to be seen as the leader in the industry. But I think that has huge potential benefits from a manufacturing cost perspective, both operationally and CapEx perspective. I'll let Stephen talk to the chemistry side of the world.
Yeah, I think what I'm finding interesting recently is how much the industry, and maybe it's just industry influencers on LinkedIn, flip-flopping between what's the next new battery chemistry. One day it's all about LMFP, but so many drawbacks and asterisks with the performance and high temperature manganese dissolution. And then all of a sudden it's sodium ion. And then all of a sudden it's LFP again. And everyone's, saying boo, sodium ion. So it's really interesting to see these competing technologies that are all these trying to eke out a little bit more energy density, but maintain long lifetime, but also be more sustainable. And we're kind of playing in this difficult triangle of like cost, safety, performance. And it's not clear what the industry is going to land on, but we're kind of spiraling around these same few types of chemistry. So I'm really interested to see where folks are going to land, what makes the most sense geopolitically and economically, and from a supply chain perspective.
Thank you, Stephen and Ken. Thanks to everyone for joining us today and for your great questions during the Q&A. We hope you found this session informative and insightful, and the recording, as I mentioned earlier, will be made available on the NOVONIX website. This is the second installment of 3 webinars NOVONIX is hosting. We're looking forward to continuing the conversation with our upcoming session on integrating impedance analysis with NOVONIX UHPC on May 14th in collaboration with Gamry Instruments. You can find registration links for this presentation on the NOVONIX website or on our LinkedIn page. You'll also be able to find a recording of our first webinar discussing our patented all-dry, zero-waste cathode synthesis process on our website or via our social channels as well. On behalf of the entire NOVONIX team, thank you once again for being here. If you have any follow-up questions or would like more information, please don't hesitate to reach out. Have a wonderful day.